Hello everyone. Today I'm going to talk about controlling parameters in the design of concrete slabs reinforced with non-metallic reinforcement, and we call them FRP-RC slabs. So this is breakdown of my presentation. I will start with giving you some background of this study, and then objectives, talking about methodology that I used, and then my observations in this design, and then some conclusions. So this is not my house. This is the one I have. This is one I have designed it. So what is special in this house? We have designed this house completely with GFRP, 0% steel, no steel. Sorry, steel guys, but it's corrosion. It's not we that we have utilized 100% GFRP bars. This building forms the basis of this study. So I will share with you my observations that I captured during design of this building. So what are the reasons that this is the first building that we are designing and not before? No one designed the building with GFRP. So I hope you have been listening in this SCI convention that GFRP have lower modulus of elasticity. It has low ductility. And possibly because of these reasons, you end up with higher initial costs and lack of design guides. And these factors actually lead to lack of confidence in the designers. And that's why I find that it's limited use in the past. And in the past, FRP only was utilized in transportation engineering or strengthening of existing structures. So what has changed? So there have been some improvement in modulus of elasticity. So people were utilizing old generation bars, and now we have moved towards new generation bars and improved bond performance. Depending upon recent research carried out at University of Scarborough, they are saying that these bars, the new generation bars, actually show better bond performance compared to old generation bars. And we have improved manufacturing techniques for those new generation bars. And availability of design guides. A new design code for GFRP bars 440 is out for public review, public comments, and hopefully that will be standard next year. So these all factors actually have improved confidence in the designers, and designers are actually thinking to utilize GFRP bars in place of steel now in the buildings as well. So now we are moving to the buildings, utilization of GFRP bars in buildings and flat works. So what are the objectives of this study? In design of buildings, we observed a few things we want to discuss with you. So the objective of this study is to understand design issues in FRP, RC slabs of residential buildings, the issues which I encountered during this design. And what are the effects of lower modulus of elasticity of GFRP bars when you are designing with FRP? And then you may be aware of chapter 7 in SCI 31819 code. It provides you a table in 7.3.1.1 where you have a relation. You can go directly and calculate thickness of slabs, but no such relation is provided in design guides and for FRP reinforcement. So I have developed that relation and I'll share with you. So as given in that table, I have analyzed the slabs for different support conditions, such as simply supported, both end continuous, one end, and cantilever slabs. Since now we don't have any software to design FRP, design slabs or anything, any member with using FRP. So we generated MathCAD sheets to analyze our slabs for different end conditions. This is just a section of a continuous slab showing the detailing of a slab. So to understand more about the issues in the design of GFRP, actually we utilize both bars, old generation bars having lower modulus of elasticity and new generation bars having more modulus of elasticity. And we utilize concrete strength of 4 KSI and 1.35 bond factor that was approved in last ACI convention. And the concrete cover was 0.75 as in the code, ACI 318 or 440 guide. So these are some observations. The code ACI 440 guide says that it is suggested that you design an over-reinforced section because you need more reinforcement to cope up with lower modulus of elasticity. Even though you have lesser stresses because you are designing an over-reinforced section, but the development length equation in the code, when you utilize that equation, you will end up with very large development length values, and it will be very difficult during construction to use those part in detailing. You will encounter some problems in construction. Due to lower modulus of plasticity, we have serviceability issues. So you will end up with more thickness of slabs compared to when you're designing with steel. So for example, if we see here, we have two options to control the deflection. Either you increase the thickness or you utilize more reinforcement. So in this slide, I have actually kept the same thickness, but I have utilized more and more reinforcement as much as I could. For example, if you see this slab here, 16-foot long slab, it has thickness of 6 inches, but you see I utilized a reinforcement of number 4 bars to maximum minimum spacing, and I wanted to put as much reinforcement as I could. So you see the required area is just 0.18 but inches square per foot, but I'm utilizing 0.94 to cope up the deflection problem. So this is the effect of having lower modulus of elasticity of GFRP bars. Either you increase the thickness or you increase the reinforcement area. So for example, if we go here and we provide the area of reinforcement, for example, it is required is 0.18 and I provide 0.39 as required by the code as a minimum reinforcement, I have to increase the thickness to satisfy the deflection problem. So designer has two options, either to play with thickness or either he has to increase the area of reinforcement to control the deflection. So deflection is a major issue when you are designing with FRP bars. I also played with new generation bars and old generation bars. Old generation bars have lower modulus of elasticity of 6,500 and new generation bars have modulus of elasticity of 8,700. It has little effect, but that is not too much dramatic that we consider them that it will control our deflection. In continuous slab, there was some advantage of having negative reinforcement at the suppose, and it increased our moment of inertia, effective moment of inertia, and somehow we were able to control deflection at lower thickness. So for example, in continuous slabs, we see if I keep the same thickness here, if I keep the thickness 5 inches and I use maximum reinforcement at the center, the required area of reinforcement is at mid-span is 0.14 and I'm utilizing 0.94 inches square per foot just for deflection control. And at the ends, we just provide the area of reinforcement just required from movement at the suppose. If I wanted to utilize minimum area of reinforcement, I had to increase the thickness. So again, I'm concluding that either you have to increase the thickness or you have to increase the area of reinforcement to cope up with this deflection problem of FRP bars. In cantilever slabs, it was really difficult to control deflection. Reinforcement never helped to control the deflection. It was the thickness. And every foot increase in length required an increase inch in thickness to control the deflection. So here is the relationship that we have developed. It might seem weird, but I'm telling you why. So for example, if you use maximum reinforcement, if you're using maximum reinforcement, you can control your deflection with this factor like L over 25. ACI says that you can satisfy deflection with L over 20. And it seems weird that FRP bars will end up with lower thickness. But this is because you are using more and more reinforcement. You are utilizing as much reinforcement as you can. And if you are using maximum reinforcement, you can actually end up with lower thickness compared to what ACI says for steel reinforcement. I also tried with minimum reinforcement here. It has like the value was more, like thickness increased, but it is more. The thickness is still smaller than what is provided in the steel code. It is because even in you are providing minimum area of reinforcement as stated by the ACI 440 guide, but still you will end up almost with the balanced reinforced section. So, I mean, you are using more area of reinforcement compared to steel. In order to understand this, why this is happening, why GFRP has slabs of lower thickness compared to steel, I actually decreased the concrete strength FC to 2500 PSI, and I use reinforcement only for flexure, and I end up with thickness is more than steel. So if you decrease the concrete strength 2500 PSI and you use the reinforcement only for flexure, you will have more thickness. But ACI 440 guide actually provides us with a lot of limitations, and in those limitations, you actually end up with more area of reinforcement, knowingly or unknowingly. So we observed that serviceability always controls the design of GFRP reinforced slabs. More reinforcement and consequently more material is required when you are designing with GFRP. Development length issues may lead to construction problems, and that equation I feel is very conservative. For example, a 12-feet slab required a development length of, for example, 2.5 feet. So it's a problem to put it in there. So it needs to be relooked. Improvements in material properties have impacted the design. So yeah, there is some effect, but that is not dramatic. Large diameter bars be avoided. So there is a problem when you are using large diameter bars. For example, even if you are using number 4 bars, you see here that the minimum area that you can utilize is 0.39 inches square. This is because the ACI 440 guide says that you have to provide more reinforcement to control cracking. Like maximum, you can provide reinforcement to a maximum spacing this one, but in satisfying that limitation, you are actually providing more area of reinforcement. So I don't know how they calculated that spacing, but that spacing is actually kills. Even if you are using number 4 bar. For example, if you are using number 5 bar, number 6 bar, imagine how much more area you will be utilizing without knowing that you are that limit. That limit is actually penalizing your design. So it's advisable to stay with as much lower area as possible, lower diameter bars as possible. And design of FRPRC slabs should be limited to 18 feet, because if you go beyond 18 feet, your thickness will be very, very large. So to avoid that, it's advisable to limit your design to 18 feet. Thank you. If you have any questions.
But I do not, I didn't get what is FRP slab means.
So FRP is actually fiber reinforced polymer.
Fiber reinforced, what's the P stand for?
Polymers.
Oh, okay,
Yeah.
okay. I get it.
So, yeah.
Okay, I get it. I get what you have like. I mean, this is really the same finding as the real reinforced concrete. You increase, you have to meet some certain criteria.
Yeah, but in
meeting
this,
the same thing.
In this, actually, you have to utilize more and more reinforcement. If you're not using more reinforcement, you will, for example, in steel, you will end up with 5-inch slab. But in FRP, if you are using reinforcement only for flexure, you will end up with 8-inch thick slab. So it's different.
Which is like quite a lot.
Yeah,
I mean, especially in the seismic area, it's quite a lot. You need to limit this.
This
slab
is what I was trying to.
Yes. Yeah. But my other question, is it beneficiary to use doubly reinforced slab?
No, this is thing we use, for example, in continuous slab, it was just for negative movements sections. Not
only.
Yeah, only. Yeah.
You don't use it for double reinforcement or anything. So, okay.
Thank you very much. I think it's really important to use novel, sustainable materials in the future, but we also need to justify use. So 2 related questions. The first one is the cost, right? You are using very expensive material, plus you are increasing the thickness of concrete, so you are really increasing the cost. I'm wondering, as compared to a traditional design, how much increase? Is it double or triple that number? I'm wondering. The second one is the justification. A project manager might tell you that we don't have corrosion problem for a properly designed slabs, right? If you have enough clear coverage in a residential construction, corrosion problem will not happen. So how would you justify increasing the cost significantly by using this material, given that you are also increasing potentially vibrations, walking vibrations, deflections, and so on? So those are the two questions.
I mean, like, maybe I'm giving the answer of the first question, and later I can answer the first. So as far as the cost is concerned, long term, I think these slabs would be cheaper. If you I was attending a session in the morning, and they were saying that in the long term, these FRP bars are much like economical compared to steel, because of their weight, because of labor costs, because of other things. But I'm not sure, because I have not calculated the that thing. But they were saying that so they are economical in long run. You are saving many things. They have more lifespan compared to steel, and they are lightweight. Your transportation cost is decreased. They are not non-corrosive and all that. And the second question, you said that I think it was like if you are using them in non-corrosive regions. For example, in Miami, this building is being constructed in Miami, so there are some chances there. For example, other cities like Karachi, or there are other cities they are really close to, or any buildings that are constructed really on the coastal regions. I think you will have problems in long run, not now, but maybe in long run, corrosion will cause some problems.
Yeah, this is actually what I want to say. It's the corrosion rust of the bars. Doesn't have it. The second, I would think it's fire, right? I mean, they must be more sustainable to fire.
Yeah.
Am I correct on this or not? I mean, I don't know.
I want to definitely want to react on this. I want to give answer of this. I was attending a session in the morning, and also according to my knowledge, according to the latest research, fire, if you have even 170 degrees centigrade, you are not having any effects on the GFRP bars, and in long run, it will not be affected by fire.